Take a look at this blueprint for a highly advanced chemical reactor. It operates with near-perfect heat transfer efficiency. It is thermodynamically brilliant. It emits zero greenhouse gases. And tomorrow, the executive board will kill the project entirely. Projects frequently collapse because they fail the critical test of economic viability, even when the underlying science is sound. To survive the boardroom, an industrial technology must satisfy the feasibility triad. It must be technically feasible, environmentally sustainable, and economically profitable. Clean technology functions as a mathematical lever designed to lower operating costs and secure a strict competitive advantage in the market. If you can design a flawlessly efficient system but cannot prove its financial return, you are functioning as a technician. True engineering requires justifying the economics of deployment. To bridge the gap between thermodynamics and corporate finance, we use a diagnostic tool called a techno-economic assessment, or TEA. This systematic framework evaluates both how well a technology performs physically and whether it makes money. We start with the technical analysis. This assesses the raw process performance, the operational maturity of the technology, and its physical reliability on the factory floor. Next is the environmental analysis, where we calculate total emissions, raw resource consumption, and the resulting carbon footprint. Finally, those physical and environmental realities feed into the economic analysis. Here, we quantify the initial capital costs, project future revenues, and calculate long-term operational savings. The TEA framework forces a translation. It takes physical realities, like heat transfer coefficients and flow rates, and converts them into the financial language of risk and profitability that decision-makers rely on. Every industrial project is split into two primary cost categories. Capital expenditure, or CapEx, covers the upfront equipment purchases, installation, and construction. Operational expenditure, or OPEX, covers the ongoing reality of running the plant: energy bills, maintenance, labor, and utilities. Look at this standard conventional industrial boiler. It presents an attractively low CapEx. It is cheap to buy and cheap to install. But because of its poor energy efficiency, it suffers from a massive OPEX. It constantly bleeds cash through high fuel consumption. Contrast that with an advanced, energy-efficient alternative. Upgrading requires a painful, significantly higher initial CapEx. However, its efficiency results in a dramatically lower OPEX year after year. This creates the OPEX paradox. Traditional purchasing logic favors the cheap unit to save budget today, but that decision masks a long-term operational hemorrhage. Lifecycle cost analysis tracks total costs over 10 years, combining CapEx, OPEX, and maintenance. The conventional boiler's cumulative cost climbs rapidly. The energy-efficient alternative starts higher, but its shallow slope quickly intersects. From then on, green technology strictly undercuts the conventional cost. The mechanism driving this shallow slope is resource efficiency, producing the exact same industrial output using fewer raw materials, less water, and less energy. Evaluating a technology based solely on a low purchase price is a mathematical error. True economic feasibility is always dictated by the lowest total life cycle cost. To secure the funding for that higher CapEx, engineers conduct a cost-benefit analysis, calculating the strict ratio of total project benefits to total project costs. The payback period divides your initial investment by annual savings, isolating the years required to recover CapEx. Next is return on investment, or ROI. Dividing net profit by investment generates a percentage, allowing executives to compare the profitability of different engineering projects. But the ultimate metric for corporate decision-making is net present value, or NPV. NPV is critical because a dollar saved 10 years from now is not worth the same as a dollar spent today. It accounts for the time value of money, discounting future cash flows back to the present rather than just tallying raw historical costs. This creates a definitive corporate rule. If the calculated NPV is greater than zero, the project creates value and is accepted. If the NPV is less than zero, it destroys value and is rejected. When you master NPV, you stop asking for favors. You mathematically prove that a multi-million-dollar clean tech upgrade is a guaranteed, highly calculated return. To see these formulas govern reality, look at the heavy materials sector. This is a Lafarge Holcim cement factory. Cement production is notoriously energy-intensive. To control operating costs, LafargeHolcim authorized a massive capital expenditure to install a waste heat recovery system directly into their kilns. The system captures extreme thermal energy that used to just vent into the atmosphere. It routes that heat to generate free on-site electricity, drastically slashing their reliance on external fuel. Applying our metrics, this massive industrial upgrade typically yields a payback period of just 3 to 6 years. After that, the electricity is pure operational profit. Now compare that heavy industrial scale to commercial real estate. Millions of facilities still rely on mundane grids of older fluorescent light fixtures like these. In a major retrofit initiative by Philips, replacing these outdated tubes with advanced LED systems yielded a 50 to 70% reduction in energy consumption. The payback period? Just 2 to 4 years. Whether you are upgrading a multi-ton cement kiln operating at thousands of degrees or swapping out a simple office ceiling light, the mechanism of competitive advantage is identical. You deploy upfront capital to crush the OPEX, accelerating the payback period. Direct utility savings, energy, water, and materials form the foundational financial return for cleantech. The hidden value lies in indirect benefits. In environmental economics, these represent the highly quantifiable financial value of improved reputation, easier regulatory compliance, and heavily reduced legal risk. Take the manufacturing floor at Interface Carpet. By pioneering material recycling and transitioning to circular manufacturing, they secured global sustainability leadership. This translated directly into increased market access and brand profitability. Toyota's cleaner production program focused heavily on water conservation and lean manufacturing. Doing so actively reduced their toxic waste treatment overhead and effectively eliminated the risk of municipal environmental fines. Now add emerging macroeconomic drivers to the ledger: rising carbon taxes, strict ESG disclosure requirements from institutional investors, and mandatory ISO 14001 certifications to even bid on certain supply contracts. In the modern regulatory landscape, minimizing your environmental footprint is a financial shield. It protects operating margins from aggressive government penalties and ensures you remain eligible for major investor capital. Let's put this into practice. You have just been appointed plant manager. Your board authorized exactly 22.5 billion rupiah for capital improvements this quarter. You have 4 competing proposals on your desk: waste heat recovery, a water recycling system, energy-efficient motors, or a solar PV system. You must choose one. Let's isolate the solar PV option and run a rapid cost-benefit analysis based on the array shown here. The technical proposal outlines a hard initial investment of 9 billion rupiah. The engineering team projects it will yield 1.8 billion rupiah in annual energy savings. Based on the formula we covered earlier, what is your raw payback period? Divide 9 billion by 1.8 billion. The system pays for itself in exactly 5 years. But a modern engineer must push the calculation further. You have to ask how indirect factors, like impending carbon reporting regulations or newly available green financing rates, might radically alter the net present value of this specific array. Effective leadership requires evaluating these competing systems not just on their megawatt output, but on their ability to bulletproof the company's financial future against market shocks. A brilliant technical design is completely useless if it only exists on paper. Real engineering power comes from mastering economic feasibility. That is how you transform sustainable ideas into unbeatable industrial realities.